Hello, this is Dr. VC Sontake and I am going to take the course Heat Transfer. Objectives of this video lecture are to explain the need of the effectiveness NTU method to analyze heat exchanger and to explain the effectiveness NTU method to analyze heat exchanger. So let us start our discussion with the effectiveness NTU method. So before going into the detail of effectiveness NTU method, one must raise a question why this NTU method is required at all. So that question can be answered by defining the limitations of the LMTD method to analyze or design the heat exchanger. The LMTD method to analyze the performance of heat exchanger or to design it is suitable and easy to use for determining the size of a heat exchanger when the mass flow rates and the inlet and outlet temperatures of the hot and cold fluids are specified or can be easily determined from specified relations. The heat transfer area and thus the size of the heat exchanger can easily be determined from the expression Q is equal to U into A into delta Tm. For example, for a given counterflow heat exchanger as shown in figure, whose temperatures are varying as shown in figure, that is, temperature of the hot fluid is decreasing from Thi to Tho and temperature of cold fluid is increasing from Tci to Tco. However, the Tco is not known and Tho is also not known. Only inlet temperatures are known. So under this condition, determination of LMTD would become difficult. However, if the inlet and outlet temperatures are not known, but the heat transfer area or size of the heat exchanger is not known, or if the type and size of heat exchanger are specified and for prescribed mass flow rates, if only inlet temperatures of hot and cold fluids are known and outlet temperatures are not known, then the determination of LMTD becomes quite difficult due to logarithmic function of LMTD. As shown in the expression for LMTD, in the denominator, the ratio of delta TO over delta TI, which is the function of inlet and outlet temperatures of hot and cold fluid both, is varying logarithmically. So if two of the temperatures are not known, the iteration would become quite complicated and involved. If LMTD method is used in such case, then the procedure would require tedious iterations and thus it is not practical. So why NTU method is required? The effectiveness NTU method is suitable for the determination of the heat transfer rate and the outlet temperatures of the hot and cold fluids for prescribed fluid mass flow rates and the inlet temperatures when the type and size of the heat exchangers are specified. So if size and type of heat exchangers are known to us and inlet temperatures and outlet temperatures are to be calculated for a given mass flow rate, effectiveness method will be very effective. An analysis of the heat exchanger can be made by effectiveness NTU method when the heat transfer surface area or size of the heat exchanger is known, but the outlet temperatures of hot and cold fluid are not known. Effectiveness NTU approach is based on the concept of capacity ratio, effectiveness, and number of transfer units. NTU. This approach facilitates the comparison between the various types of heat exchangers which may be used for a particular application. So for a given heat transfer rate, which type of heat exchanger will give the minimum size, that can be decided by applying the effectiveness NTU method. So before further going into the detail of effectiveness NTU method, let us define some fundamental terms which will effectively describe the effectiveness NTU method. And in this series, the first term is capacity ratio. The dimensionless quantity called the capacity ratio, capital C, is defined as the ratio of minimum to maximum heat capacity rate of the two fluids. So mathematically, capacity ratio is equal to capital CP minimum to the capital CP maximum, where the minimum heat capacity rate, capital CP minimum, is the product of m dot Cp under minimum condition, and its unit is watt per Kelvin, and maximum heat capacity rate, capital Cp max, is equal to m dot into Cp under maximum condition, and unit is watt per Kelvin. The second term is effectiveness of heat exchanger. Effectiveness of heat exchanger is defined as the ratio of actual heat transfer rate to the maximum possible heat transfer rate between the two fluids. Mathematically, effectiveness, represented by epsilon, is equal to ratio of actual heat transfer rate to the maximum possible heat transfer rate between hot and cold fluid, is equal to Q actual over Q max. In case of heat exchanger, under steady state condition, actual heat transfer rate can be given by Q actual is equal to heat transfer rate given by hot fluid is equal to m dot H Cph into Thi minus Tho is equal to Cph into Thi minus Tho, where Cp, capital Cph, is the product of m dot H into Cph. Small Cph is the specific heat of hot fluid. Actual rate of heat transfer can also be given as the heat transfer rate taken by cold fluid, Qc, is equal to m dot C small Cpc into Tco minus Tci is equal to capital Cpc into Tco minus Tci. Capital Cpc is the heat capacity rate of cold fluid. The heat transfer in a heat exchanger will reach its maximum value only for maximum possible temperature difference. And the maximum possible temperature difference is given by temperature difference between Thi minus Tci. This is the maximum possible temperature difference available to any heat exchanger. Now the temperature difference will reach its maximum value to make the heat transfer rate maximum under following conditions. When the cold fluid is heated to the inlet temperature of the hot fluid, that is Tco is equal to Thi. When in the figure there is a parallel flow heat exchanger with hot and cold fluid temperatures as Thi and Tci respectively, so the temperature difference will be maximum when Tco is equal to Thi, or the hot fluid is cold to the inlet temperature of the cold fluid, that is Tho will be cooled down to the initial temperature of cold fluid. Tho is equal to Tci. Under both these two conditions or either of the condition, heat transfer rate will be maximum in a particular heat exchanger. However, these two limiting conditions of maximum possible temperature difference will not be reached simultaneously unless the heat capacity rates of the hot and cold fluids are identical. That is, heat capacity rate of cold fluid is equal to heat capacity rate of hot fluid. Now when capital CC is equal to capital CH, which is the real case or practical case, the fluid with the smaller heat capacity rate or the fluid with the minimum heat capacity rate will be the first fluid to experience the maximum temperature, at which point the heat transfer will come to a halt. Therefore, the maximum possible heat transfer rate in a heat exchanger is Qmax is equal to capital Cp minimum into Thi minus Tci. Now you can also understand this in by the example, like there are two persons. One can give 5 lakh rupees to another person, but the second person is willing to take only 2 lakh rupees. So what is the maximum possible amount of transaction? It is 2 lakh rupees only. Similarly, the concept of maximum heat transfer rate. The maximum possible rate is possible only to the heat capacity rate of fluid having minimum heat capacity rate. Hot fluid can give maximum heat, but if cold fluid can receive only some portion of that heat transfer, so maximum possible rate will be equal to the minimum heat capacity rate of the fluid into maximum possible temperature difference available. In this case, Cp minimum is the smaller of Cph and Cpc. After finding out the product of m dot Cp, whichever value is lower, that will be Cp minimum value. So this expression for effectiveness can be obtained in terms of cold fluid and hot fluid. So for cold fluid, effectiveness is the ratio of Q actual to the Q max. For cold fluid, Q actual will be heat transfer rate taken by the cold fluid is over Q max. QC will be m dot C Cpc TCO minus TCI, and Q max is m dot Cp minimum into Thi minus Tci. So effectiveness is equal to m dot C Cpc TCO minus Tci over capital Cp minimum Thi minus Tci. Expression for effectiveness in terms of hot fluid is effectiveness is equal to Q actual by Q max. For hot fluid, Q actual will be heat transfer rate by hot fluid QH over Q max. The expression for QH is m dot H Cph into Thi minus THO, and for Q max m dot Cp minimum into Thi minus Tci. So effectiveness is equal to m dot H Cph Thi minus THO over capital Cp minimum Thi minus Tci. The last term is number of transfer units, NTU. The effective relations of the heat exchangers typically involve the dimensionless group, which is called the number of transfer units, NTU, and is expressed as NTU is equal to U into AS over capital Cp minimum is equal to U into AS over product of m dot Cp under minimum heat transfer rate condition. In this expression, U is the overall heat transfer coefficient in watt per meter square Kelvin. AS is the heat transfer surface area of the heat exchanger in meter square. And Cp is the specific heat and capital Cp is the heat capacity rate. From this expression, NTU is directly proportional to AS. That is, for a specified value of U and capital C minimum, the value of NTU is a measure of the physical size that is heat transfer area of the heat exchanger. Thus, the higher the value of NTU, the larger the physical size of the heat exchanger. So from the value of NTU, I can predict the size of the heat exchanger to transfer a particular rate of heat transfer. So it can be shown that the effectiveness of a heat exchanger is a function of the number of transfer unit and the capacity ratio C. So effectiveness is a function of UA over C minimum and ratio of C minimum to C maximum. That is function of NTU and capital C. Now we can find out the relationship between effectiveness epsilon and NTU and capacity ratio for parallel flow heat exchanger and counter flow heat exchanger. So effectiveness for parallel flow heat exchanger expression can be given as epsilon parallel flow is equal to 1 minus exponential of minus UA over C minimum into 1 plus capital C minimum over C maximum over 1 plus ratio of C minimum to C max. Here UA over C minimum is NTU and C minimum by C maximum is capacity ratio capital C. So epsilon parallel will be equal to 1 minus exponential of minus NTU into 1 plus C over 1 plus C. Similarly, effectiveness for counterflow heat exchanger, epsilon counterflow is equal to 1 minus exponential minus NTU into 1 minus C over 1 minus capital C exponential of minus NTU into 1 minus capital C. Now, the expression for effectiveness for parallel and counterflow are shown in the slide. No need to remember these two formulae because these two formulae are given in the heat transfer data book by CP Kothandaraman. Learning outcomes of this video. After watching this lecture, the learner will be able to explain the need of the effectiveness NTU method to analyze heat exchanger and will be able to explain the effectiveness NTU method to analyze the heat exchanger. With this, I come to an end of this video lecture. Thank you for your kind attention and passionate listening. Happy learning.